as we get to the end of this unit, we're going to be solving equations. And then the last part of this unit is going to be using the skills of solving equations to solve and solve some real-life application problems. Okay, so to solve equations, we are going to focus on 5 major categories that we're going to run into for how to deal with getting rid of a logarithmic equation or an exponential equation. The first one's the one-to-one properties. That's the properties you used when you did your very first worksheet with exponentials in 4.1. We're going to extend that idea to logarithms. Then we're going to isolate, use order of operations backwards. When we get stuck on a logarithm or an exponential, we're using the definition of logs, converting Ben to Benny. Then we'll get into what if we have more than one logarithm at a time and we can't use our one-to-one property? Well, we can condense it to a single logarithm, and then we go back to isolation. We can have quadratics in disguise, which will often take us right back to that isolation idea after we solve for our u. And what if we have more than one exponential? Well, this is where we're actually going to drop in a log. We'll take a log and we will expand. Now, these are the issues of how to deal with the logarithm. Other stuff can be mixed in with this. So we might have to still follow the factoring hand. Okay, so some things will still apply that are old stuff, but these are the 5 things we'll deal with when we have a logarithm. The other part of the goal is not just know how to solve it, but make sure your answers are okay to keep. Know how to check for what we call extraneous solutions. So we are trying to stay with real numbers and real solutions. Okay, so we won't deal with anything that's going to bring us into the imaginary numbers or complex playing with this section right here. All right, so let's talk about extraneous solutions. The old stuff were rational equations, and on those problems you just had to make sure the denominator was not equal to 0. Then we had even roots, and we had to actually go and plug them back in and check to make sure we got a true statement. Well, with our logarithms, the issue that we're going to have to deal with, it's more like the rational equations where you can just look at the original problem, know what you're not going to accept at the beginning. Every n from Benny, the number that we put inside the logarithm, that value has to be greater than 0. Notice I didn't say x, so the number inside the logarithm, and it has to be in the original equation. When you condense, you're going to change that value of n sometimes, and you'll let numbers sneak in that shouldn't be answers. All right, so the one-to-one property, it's saying set the e's equal or the n's equal. So if you're dealing with an exponential, we are setting the exponents equal. If you're dealing with a logarithmic equation, you're setting the numbers equal to each other. This is only true if you just have an exponential equal to an exponential and they have the same base. Same thing's true when you have a log equal a log, as long as they have the same base. So the one condition on both of these is that you have to have the same base. So let's look at a couple examples for this first category. The one on the left is something we would have seen from our worksheet way back when on our very first day of notes. So we can rewrite these both as powers of 2. So we got 2 cubed is 8. We're going to multiply the powers together. So when you raise a power to a power, you multiply them. Parentheses are important. We got 2 to the 4th times x plus 3. Now that the bases are equal, then we can set the exponents equal to each other. So we have 9x minus 3 after we distribute equal to 4x plus 12. We're going to collect our x's on one side. So let me subtract that 4x over. We're going to add the 3x or the 3 to the other side. We get 15. We got x equals 3. I have no worries about extraneous solutions on this problem. I shouldn't have any. If I check it and it doesn't work, then I've made an error. I'm worried about the logarithm problems. So the next example is the one I'm going to have to remind myself to check for extraneous solutions. These values have to be positive after I get my answer. All right, So in this one, it's nicely set up for us. We have two logarithms equal and they have the same base. Since they have the same base, we can set those numbers, those n's, equal to each other. All right, we got an x and an x squared, so I'm going to move everything to one side and solve by factoring. So I'm going to leave the 4x squared alone. I'm going to add the 7x over, which cancels out that 7x, and then I'm going to subtract the 9. Now, you could say, hey, I see x only once and use the order of operations and isolate. Or you can factor and solve. Your choice. If you factor, you tend not to forget one of the two possible answers. So we got 2x plus 3. 2x minus 3 equals 0. So x is negative 3/2, and x is positive 3/2. Now, before I go and say, hey, got my answer, let's move on, I check for extraneous solutions. You may use the power of the calculator to help you out a little bit, or you can do it by hand. So I'm just going to take my negative 1.5, I'm going to plug it into both the equations, make sure they're going to be positive. So 4 times negative 1.5 squared minus 7 times 1.5. Sorry, negative 1.5. That's positive. We accept this answer. Then I'm going to check positive 1.5. That's negative. This is extraneous right here. Now, I could have checked it by hand and said, okay, we're timesing by 1.5, and 7 times 1.5 is what? 10.5? 9 minus 10.5 is a negative. So you don't have to use the calculator. If you can see the numbers in your head, that's fine. This is what we call an extraneous solution because it's dealing with imaginary concepts. Log base 5 of a negative is an imaginary value. So we're just going to stay away from imaginary numbers in our logarithms. That brings us to the second category, isolation. So isolate your exponential or logarithmic form, order of operations backwards, then convert. So the big idea of converting is what we did in section 4.3. We convert from Ben to Benny. Remember, they're equivalent equations. They're just written different ways, like Ben and Benny are the same name for the same person. Okay, we go from exponential to logarithmic or logarithmic to exponential. After you do that, you continue to isolate. If your original problem starts with a log, you must check for extraneous solutions. So let's go ahead and start with the logarithm. So what we're going to do is we're going to try to get this by itself because then I can convert using the definition. So I'm going to add 3 first. Then I'm going to divide by 5. So we have log base 3 of x squared minus 8x equals 2. So here's where I normally get to the person that I know really doesn't understand this chapter and they try to times each side by 3. No, we're going to use an exponent to get rid of it. And logs equal exponents, so we know we have something squared. The base is the same base, so it's base of 3. And then we're going to set this equal to x squared minus 8x. At this point in time, we should be doing review of Algebra 2 or College Algebra A, whatever was your previous math class, or our Chapter 1. So we got an x squared and an x, so we're going to set it equal to 0. Let's move things so x squared is positive. So I'm going to subtract that 3 squared, which is 9. Then we're going to factor. So we have x minus 9, x plus 1. We come up with x equals 9, x equals negative 1. We started with the log, so we're going to go back to the original problem, and we're going to check for extraneous solutions. So what we really just have to make sure is that this x squared minus 8x is positive. So 9 squared minus 8 times 9. 9 nines minus 8 nines is 1 9. That's positive. The negative 1 squared is 1. minus 8 times negative. That double negative makes a plus. So 1 plus 8, that's positive. So both answers work in this problem. All right, let's move on to the exponential function. So again, our goal is to isolate the exponential or logarithm first, so we can get in the form of Ben in this problem. So I'm going to subtract 1, and then we're going to divide by 2. Okay. So subtract 1, we get 10, divide each side by 2, and we have it equal to 5. So we have 7 raised to the 4x plus 3 equals 5. So now we convert. So we have log base 7, logarithms equal the exponent, so we're going to have a set equal to 4x plus 3. And then we're going to solve. So we're going to take log base 7 of 5 minus 3, and then divide the whole thing by 4. This is what's known as the exact solution. So when you're asked for the exact solution, there's a couple of ways you could write this. You could distribute that fourth through both of them. You could also use change of base. So you could change that log base 7 to a log or a natural log, your choice. And then distribute that 1/4 through. So this is also the exact solution. Again, you could have used any log, any base that you want when you do change of base. If I want to put it as a decimal, so if I have a calculator and they ask for to so many decimal places, I just can plug it in. I'm going to go use this form since my calculator can do log base 7. So I'll start with my fraction line, alpha window, and then I'm going to do alpha y equals to get to the fraction. Alpha window number 5, log base 7 of 5. Make sure you close that parentheses or get out of there before you subtract 3. We're not doing log base 7 of 2. Divide that whole thing by 4. And we get negative 0.5432. And you just go to how many decimal places they ask. Now, if you want to check your answer to see if you actually did it without making an error, that answer is stored in as answer. So what I'm going to do is I'm going to just do 2 times 7 to the 4 times my answer, so second negative, plus 3, and then I'm going to add 1. Should get 11 or something that rounds really, really close to 11, depending on how accurate this takes it out to it. And it gets exactly 11. So I feel confident with my answer. And there should not have been an extraneous solution on this one. So if you check, you're just checking for your own errors. All right, category C, the third type. It's when we have many logs on one side, and we have something that's not in a log. If we can get it down to a log equals a log, we can make it a category A problem. When we have log plus log equals not a log, or a log minus a log equals a number, or something like that, what we can do is condense first. So when you condense, sometimes you're going to have to move all the logs to the same side, and everything without a log to the other side. Then condense those logarithms that are on the same side, like we saw with the properties from 4.4. Then at that point in time, you just ask Ben and Benny for help. So when you get stuck at the very end, you're like, how do I get rid of this log? You're going to go and change it from Benny form to Ben form, from logarithmic form to exponential form. All right, so we're adding 2 logs, means multiply the inside. So we're going to FOIL out x plus 3 times x minus 1. We get x squared plus 3x minus 1x, and then a negative 3. Okay, at this point I'm stuck at the log, so I convert it. So I use my base raised to my exponent. Remember, logs equal exponents. And that base raised to an exponent equals my number. So we're going to bend form, or exponential form. Set equal to 0. You can solve by quadratic formula, or factoring, or completing the square. This one factors nicely. And I come up with x equals -4, x equals 2. But note, we started with a log. So what should we always do when we start with a log? Check for extraneous solutions. So we just have to make sure the underlying piece is going to be positive. Well, if I plug in -4, that's going to be a negative. Okay, so that one's extraneous. And this right here has to be positive. When I plug in 2, it's positive. When I plug in 2 over here, it's positive. Both of them got to be positive. So 2 works. All right. Looking at the other one, the problem right now is I can't condense because the logarithms are not on the same side of the equal. So I'm going to have to subtract that logarithm to move it over. These problems will definitely be on the test. When I subtract 2 logs, I can condense it to a single log by dividing the end part from Benny. Now I have a base. There's my number. Here's my exponent. So I'm going to convert it so I can get the end part from this logarithmic form by itself, because that's where the variable is. All right, we're no longer dealing with a logarithmic equation. We're dealing with a rational equation. So let's clear our fractions. Let's multiply each side by x plus 9. So this is 9 times x plus 9 equals 11 x plus 7. Distribute, collect like terms, and solve. So I'm going to go ahead and move the x's to the right, subtract 9x, and then I'll subtract 7. Divide by 2 and I get 37 is x. Don't forget that we are going to need to check to make sure that the original problem, when I put in 37, this is going to be positive. So 11 times 37 is positive, and if you add 7 to that, you get a positive. Positive 37 plus 9 is positive. So it's not extraneous. Two more categories to go. The next one we're going to go revisit, quadratics in disguise. I really should have a U here. And here. So when we see this, it looks kind of like a quadratic. Our base is probably going to be some type of logarithm or exponential. I want you to realize when you have something that looks like this, a log quantity squared, you cannot take that 2 and bring it out. This means log base b of n times log base b of n. You can't bring the 2 out. You can bring the 2 out if you had log base b of n times n. That'd be log base b of n plus log base b of n. That's 2 of them, or squared here. So where the parentheses are, where you see them, that makes a huge difference. Okay, if you see an exponent that is even, you can always break that out to quantity squared. So let's take a look at the next set of problems. What we're looking for is 3 terms, one that's a constant, which we have, and then the other ones have the same base, and one of them is twice as big as the first. We're not going to be too tricky. One's going to be squared and one's going to be the first power. So what we're going to do is we're going to replace this problem, let u equal log base 2 of x. So 3u squared minus 8u And since we're dealing with quadratic in disguise, I'm going to move everything to one side. So I'm going to add this 5 over. So now we're looking for factors of 15 that add up to be -8. So that's -3 and -5. You can rewrite the middle term and do your Marf method. I'm going to go a little bit faster with this. I'm going to go and do the factor in your head method, or you can use the down under, fly over, whatever method you want to use. There's only one way to get 3u squared. That's 3u times u. I need to get a -3 as one of my outer or inner products. Well, that's only one way to do that. 3 times -1. So I'm going to do 3 times -1. I need a -5 for my other product. So I got my outer is -3. My inner is going to be -5. So that's 1u times -5. So at this point in time, if you're good with factoring, you don't have to show the work. You can just factor. Okay. If at this point in time, college algebra, you've done this enough. If you need to rewrite it and do Marf and group, then do so. So I'm coming up with u equals 5/3 and u equals 1. So as far as this problem goes, I'm only about 40% of the way. This would give me 2 out of 5 on the test. I need to show that I'm actually solving for a logarithm. Okay, the quadratics in disguise we've done before. So I need to substitute back, which is still not getting me any extra points at this point in time, but it's going to help me get there. Now I'm going to have to attempt to get x by itself. So I'm stuck at this logarithmic form. I'm going to go to exponential form. I see my base is 2. Logs equal exponents. So that means the n is actually the x value. So 2 to the 5/3 equals x. There's my exact answer. If I want to, I can use a calculator to get a decimal. So 2 raised to the 5/3. So 3.1748. And I should make sure this is not going to be extraneous. This one's easy. It's just x for our number. So that just has to be positive, so this one's good. All right, for this other one, it is 2 to the 1st equals x, so x is 2. And it is going to make our n positive, so we are good. It makes both ends positive. All right, our next problem, very similar. This one's already equal to 0. So in this problem right here, we see that we have our u is e to the x. This really is 3e to the x squared minus 5 times e to the x plus 2. So we are going to use our u substitution and really solve for the problem 3u squared minus 5u plus 2 equals 0. So we're looking for something that multiplies to be 6 and adds to be -5. So same sign, both got to be a negative. So 2, -3, -2 and -3 are our numbers. So we have 3u times something with a u equals 0. I need a -3, so it's got to be -1. I need this one to be a -2, so -2 here. Make sure we're having the same problem. That's +2 for the constant. U squared is 3u squared. And we just checked with the -3u and the -2u is -5u. So u equals 2/3. U equals 1. And now we substitute back in terms of our e to the x. So e to the x is 2/3. E to the x is 1. If at any point in time you have e to the x equals a negative number, you know you can't solve that. E to the x has to be greater than 0. Okay, so if you factor out an e to the x, and that's what you're going to see in the homework, Could be a fair game for the test and the quiz. If there was another e to the x as a factor of everything, then you can factor it out. That's just following the factoring hand using GCF. That won't give you any solutions when it's equal to 0, though. All right, so now we convert. So we take log base e, which is the natural log, of our number 2/3 equals the exponent. So that is the exact answer, natural log of 2/3. The other exact answer, that would be the natural log of 1 equals x. I do expect you to simplify that one. That's 0. We got a rule in our properties. Log of any base of 1 is 0. If I ask for so many decimal places on the test, then you have to give me the natural log of 2/3. That's the correct decimal value. I do not have to worry about any extraneous solutions because this problem was originally an exponential. Again, you can round or truncate, so this last one can be a 4 or a 5. I don't care. That's good enough. All right, the last category. I like to call this one the sledgehammer. You're just going to have to hit something really, really hard to make this one work. So what if you have something like our very first problem where you have a number to a power with a variable equal another number with a power? But unlike the first problem, when we use something like an 8 and a 16 as our bases, which were both powers of 2, we'll use something like 8 and 7, things that are not going to be powers of the same base. So in this case, what you're going to do is you're going to take any log. Me personally, I just take the natural log, or you can take the common log. If you do that, then you don't have to worry about doing change of base at the end of it. But you could do log base 7, log base 2. I don't really care. It won't matter. Once you take the log to the side, you're going to expand the equation. And the expansion rule you're going to use, you're going to take whatever power you have and you'll drop it in front of your log. Then you're going to isolate. A couple things I want to warn you of and make sure you realize. Natural log of 2 is just a number. So when you start seeing this, you're going to see some weird numbers like natural log of 2. So we'll eventually get to something that looks like 2x plus 3 equals 7. That's easy. Subtract 3, divide by 2. Except for it'll be more like x natural log of 2 plus the natural log of 3 equals the natural log of 7. Okay, then you subtract the natural log of 3, then you divide by the natural log of 2. Don't treat these numbers different than any other number. We will not discriminate against our irrational numbers. They get treated just the same as every other rational number. All right, we'll only do one example here. On the right side, I'll write down kind of a step-by-step process that we're going to do. So the first thing we're going to do is we're going to take a logarithm of each side. I'm going to choose the natural log. So take the natural log of each side. So I'm going to take the natural log of 3 to the negative 2x plus 1, and I'm going to take the natural log of 2 raised to the 5x minus 7. That's our first step. Our next step is we're going to expand. We're going to bring the exponent out in front. And when you do this, make sure that you take the exponent and put it in parentheses if it has more than one term. So both of these have more than one term. So I'm going to put those exponents in parentheses right now so I don't mess this up. All right, so we're going to do this, and now we have negative 2x plus 1 times just the plain weird number natural log of 3, which is 1 point something. And then the quantity 5x minus 7, and we're going to times it by the weird number 0 point something, which is natural log of 2. Those are just numbers. So if you got rid of the natural log, if you weren't looking at the natural log, you would just take the 3 and distribute and the 2 distribute. That's what we're going to do. Except these numbers are kind of like square roots of 2. It's just easier to leave it as square root of 2. So we're going to leave these as natural log of 3, natural log of 2. All right. So now we're going to distribute. So we have negative 2x natural log of 3 plus natural log of 3 equals 5x natural log of 2 minus 7 natural log of 2. All right. So I have two terms with x and two terms without x. So what I'm going to do is I'm going to collect variables on one side and terms without variables, or the non-variables, on the other. We've done this skill many times since Algebra 2. Most recently, we would have seen this when we were finding the inverse of a rational function. So I'm going to go ahead and move my x's to one side and my constants to the other. I prefer adding, so I prefer to take this term and add it over here. And this term, I'll add it over here. You can put your x's on the left and your constants on the right. It doesn't matter. We'll have the same answer. So I'll have the natural log of 3 plus 7 natural logs of 2. And that is equal to 5x natural log of 2 plus 2x natural log of 3. All right, I need to get it where I see x only once so I can isolate. Well, x's have the same power, so this will not be so tough to do. What I'm going to do is I'm going to factor out just the x, nothing else. Not doing a GCF, I'm just factoring out the x. And then to solve, I will divide by the number in front of x. I'll leave the left side alone. Sometimes solution keys get a little crazy and they start condensing, and they might do 2 to the 7th and get that number, which is 128, and times it by 3 and just write it down there. We're not going to require that. But if that's what the solution key is doing, then at least you can follow. We're going to factor out our x. Somebody might rewrite this as natural log of 32 plus natural log of 9. They might go and pop the powers up, and then they might condense it. I'm not going to do that. I just want to get my answer. So now I'm going to divide each side by this number right here. X times 5, I divide by x. So x times square root of 2, I divide by square root of 2. So x times this number times the number plus a number times a number, that's just a number. Divide by it. If they say write the exact solution, you're done with the problem. If they say round it, then we can use our calculator. So, or if they say write it to so many decimal places. So I'm just popping my fraction key. If you don't have a fraction button on your calculator, then you can use parentheses, type the entire numerator, close the parentheses, and hit the divide button. All right, so we have the natural log of 3 plus 7 natural log of 2 all over 5 natural log of 2 plus 2 natural log of 3. If you don't like the natural log, you could always use common log instead. Just use the same logarithm. This is 1.0508. Depends on how many decimal places you're told to go right to. 1.0508. Often we'll ask for at least 3 decimal places. So I were you, I'd make sure I study the step-by-step instructions on the right to give you a process on this problem, and then practice it. This is definitely what makes this a college algebra type unit rather than just redoing what we did in Algebra 2. So for your homework, there are only, we got some book assignment problems here. Make sure you practice these. The quiz that I would give you 5 problems. I try to make sure I hit all the different categories.